Yeah, Mr. Robert Davies from University of York in the United Kingdom, who work on exploring the physics of kinetic ballooning modes.
Hi, I'm Bob Davies, and I'll be talking today about my research, the study of small-scale plasma turbulence using gyrokinetics. The motivation, big picture, is to better understand turbulence because it largely determines the performance of magnetically confined fusion devices. So a simple picture of how instability, turbulence, and fusion power are linked, shown here. The idea is that instabilities are triggered if the gradients in the plasma exceed some limit, so density, temperature, pressure, and this causes turbulence and hence turbulent transport, which in turn will flatten the profiles. Of course, because instabilities regulate the profile, they likely play a role in things like the Elm cycle. So how and when do edge localized modes occur, and how does the plasma evolve between elms? So by studying micro-instabilities, we might be able to reduce the impact of disruptive events. And we can study these instabilities using gyrokinetic simulations. And it is helpful to understand a little bit where the theory comes from. So we start off with a completely accurate, but numerically intractable Vlasov equation, and we make some physically motivated simplifications. We end up ultimately with the gyrokinetic equation, shown here. The details are not supremely important, but H is the distribution function, which tells us about plasma fluctuations, and it evolves in time according to various physical effects shown here. Now, we can write the gyrokinetic equation as a linear operator acting on H, which is easy to solve, and a nonlinear operator, which is difficult to solve computationally. Physically, the nonlinear term corresponds to fluctuating electromagnetic drifts acting on H. So what if, for now, we just ignore this nonlinear term? Well, if we ignore the nonlinear term, we get a solution for H, which will either grow or decay exponentially in time. So this is telling us about instability growth rates. And we can see how this varies as we change various plasma parameters. So a first interesting result is from some research I've done in collaboration with Tiamat in Madrid. We looked at instabilities in Wendelstein's 7x plasmas. Specifically, how do instability growth rates depend on the density gradient and the temperature gradient? And so one can look at the growth rate as a function of these two variables, which is shown in the plot here. And the interesting thing to note is that the growth rate is lower, so the plasma is more stable, if the density and temperature gradients increase but stay approximately the same. So this is an exciting and interesting result, which is an area of active research. I should point out that this has assumed no magnetic fluctuations. In cases where the plasma beta becomes large, magnetic fluctuations are important, and they give us electromagnetic instabilities, which is quite important for high-performance devices. And one particular electromagnetic instability I've been looking at is the kinetic ballooning mode, or KBM. The details are not supremely important. Suffice to say that it tends to be unstable at high plasma beta or where pressure gradients are large. So this is in the fusion-relevant regime. And I've done some simulations to look at how KBMs behave in tokamaks, which I'll show you now. The interesting thing to look at is how the instability growth rate varies as a function of magnetic shear and pressure gradient. And we can also compare our gyrokinetics to a highly idealized instability called the ideal ballooning mode, which comes from MHD. And this is a very simple test case called the cyclone base case. And we see that there's a region of parameter space where the growth rate is high, and this matches quite closely the red line, which is IBM stability boundary. The next thing I looked at is to see how the instability changes as we change the shape of the plasma. So for a spherical tokamak test case, I tried changing plasma triangularity, and we see that positive triangularity is good news for KBM stability, and negative triangularity is bad news. This could be relevant for the STEP reactor in the UK, for example. So to summarize, so far, we can use linear gyrokinetic simulations to look at plasma instabilities, and there are some interesting electrostatic stellarator results, and some interesting electromagnetic tokamak results. The results so far have been linear because we've ignored that nonlinear term that I mentioned earlier. This is informative, but if we want to find out about fluxes, particles, and heat, we need to include this nonlinear term. But the nonlinear term creates some problems for reasons we'll soon see. So just to recap, a physical picture of the nonlinear term is that as the plasma fluctuations grow, okay, they're going to generate fluctuating electromagnetic fields. And these fluctuating fields are going to interact with the plasma fluctuation through things like E cross B shear, and it's going to result in the fluctuations saturating. Mathematically, it looks like this. Details, once again, not important, but we can see that there's electromagnetic fluctuations in blue, and we can also see this V parallel in orange. This represents particles streaming freely along the perturbed magnetic field. And streaming, of course, is quite fast, and this creates problems in current codes because there's a time step constraint, which makes the electromagnetic simulations grind to a halt. We're hoping to eliminate this using a novel numerical approach called interpolation-free semi-Lagrangian. Feel free to chat with me for more details and watch this space. So to summarize, gyrokinetic simulations are really good, and hopefully they'll get even better quite soon because of new numerical approaches to permit fast, nonlinear electromagnetic simulations. And if this sounds cool, I'd love to hear from you. So please drop me an email, and thank you for listening.
Thank you very much, Bob, for the wonderful talk.